everyone. Sorry for being late. Welcome to our very first Analyst Day for Autonomy. I really hope that this is something we can do a little bit more regularly now to keep you posted about the development we're doing with regards to autonomous driving. About 3 months ago, we were getting prepped up for our Q4 earnings call with Elon and quite a few other executives. And one of the things that I told the group is that from all the conversations that I keep having with investors on a regular basis, the biggest gap that I see with what I see inside the company and what the outside perception is our ability of autonomous driving. We've been working on the new full self-driving chip. We've had a complete overhaul of our neural net for vision recognition, etc. So now that we finally started to produce our full self-driving computer, we thought it's a good idea to just open the veil, invite everyone in, and talk about everything that we've been doing for the past 2 years. So about 3 years ago, we wanted to find the best possible chip for full autonomy. We found out that there's no chip that's been designed from ground up for neural net. I invited my colleague Pete Bannon design such chip for us. He's got about 35 years of experience of building chips and designing chips. About 12 of those years were for a company called PA Semi, which was later acquired by Apple. So he worked on dozens of different architectures and designs, and he was the lead designer, I think, for Apple iPhone 5 just before joining Tesla. And he's going to be joined on the stage by Elon Musk.
Actually, I was going to introduce Pete, but Martin's done so. Pete's just the best chip and system architect that I know in the world, and it's an honor to have you and your team at Tesla.
Thanks, Elon. It's a pleasure to be here this morning, and a real treat, really, to tell you about all the work that my colleagues and I have been doing here at Tesla for the last 3 years. I was hired in February of 2016. I asked Elon if he was willing to spend all the money it takes to do full custom system design. And he said, well, are we going to win? And I said, well, yeah, of course. So he said, I'm in. And so that got us started. We hired a bunch of people and started thinking about what a custom design chip for full autonomy would look like. We spent 18 months doing the design, and in August of 2017, we released the design for manufacturing. We got it back in December. It powered up, and it actually worked very, very well on the first try. We made a few changes and released a B0 Rev in April of 2018. In July of 2018, the chip was qualified, and we started full production of production quality parts. In December of 2018, we had the autonomous driving stack running on the new hardware, and we were able to start retrofitting employee cars and testing the hardware and software out in the real world. Just last March, we started shipping the new computer in the Model S and X, and just earlier in April, we started production in the Model 3. So this whole program, from the hiring of the first few employees to having it in full production in all 3 of our cars, is just a little over 3 years, and is probably the fastest system development program I've ever been associated with, and it really speaks a lot to the advantages of having a tremendous amount of vertical integration to allow you to do concurrent engineering and speed up deployment. In terms of goals, we were totally focused exclusively on Tesla requirements, and that makes life a lot easier. If you have one and only one customer, you don't have to worry about anything else. One of those goals was to keep the power under 100 watts so that we could retrofit the new machine into the existing cars. We also wanted a lower part cost to enable full redundancy for safety. In terms of actually doing the chip design, as Elon alluded earlier, there was really no ground-up neural network accelerator in existence in 2016. So we set out to do that ourselves. Another thing that was a little unexpected when I first arrived was our ability to leverage existing teams at Tesla. Tesla had wonderful power supply design teams, signal integrity analysis, package design, system software, firmware, board designs, and a really good system validation program that we were able to take advantage of to accelerate this program. Here's what it looks like. Over there on the right, you see all the connectors for the video that comes in from the 8 cameras that are in the car. You can see the 2 self-driving computers in the middle of the board, And then on the left is the power supply and some control connections. Various elements. You have video, computing, and power. It's straightforward and simple. Here's the original hardware 2.5 enclosure that the computer went into. Here's the new design for the FSD computer. It's basically the same. That, of course, is driven by the constraints of having a retrofit program for the car. I'd like to point out that this is actually a pretty small computer. It fits behind the glove box, between the glove box and the firewall in the car. It does not take up half your trunk. As I said earlier, there's two fully independent computers on the board. You can see them there highlighted in blue and green.
And if I can add something, the general principle here is that any part of this could fail and the car will keep driving. So you could have cameras fail, you could have power circuits fail, you could have one of the Tesla full self-driving computer chips fail, car keeps driving. The probability of this computer failing is substantially lower than somebody losing consciousness.
One of the things additional thing we do to keep the machine going is to have redundant power supplies in the car. The cameras are the same, so half of the cameras run on the blue power supply, the other half run on the green power supply, and both chips receive all of the video and process it independently. So in terms of driving the car, the basic sequence is collect lots of information from the world around you. Not only do we have cameras, we also have radar, GPS, maps, the IMUs, ultrasonic sensors around the car. We have wheel ticks, steering angle. We know what the acceleration and deceleration of the car is supposed to be. All of that gets integrated together to form a plan. Once we have a plan, the two machines exchange their independent version of the plan to make sure it's the same. And assuming that we agree, we then act and drive the car. Moving on to talk about the full self-driving chip a little bit. And lastly, there's a safety system, and basically the job of the safety system is to ensure that this chip only runs software that's been cryptographically signed by Tesla. If it's not been signed by Tesla, then the chip does not operate. Moving on to results. We had a goal to stay under 100 watts. This is measured data from cars driving around running the full autopilot stack. We're dissipating 72 watts, which is a little bit more power than the previous design, but with the dramatic improvement in performance, it's still a pretty good answer. Of that 72 watts, about 15 watts is being consumed running the neural networks. In terms of cost, the silicon cost of this solution is about 80% of what we were paying before. So we are saving money by switching to this solution. And in terms of performance, we took the narrow camera neural network, which I've been talking about, that has 35 billion operations in it. We ran it on the old hardware in a loop as quick as possible, and we delivered 110 frames per second. We took the same data, the same network, compiled it for hardware for the new FSD computer, and using all 4 accelerators, we can get 2,300 frames per second processed. So a factor of 21.
It's night and day.
I've never worked on a project where the performance increase was more than 3. So this was pretty fun. If you compare it to, say, Nvidia's Drive Xavier solution, a single chip delivers 21 teraops. Our full self-driving computer with 2 chips is 144 teraops. To conclude, I think we've created a design that delivers outstanding performance, 144 teraops for neural network processing. It has outstanding power performance. We managed to jam all of that performance into the thermal budget that we had. It enables a fully redundant computing solution. It has a modest cost. And really the important thing is that this FSD computer will enable a new level of safety and autonomy in Tesla's vehicles without impacting their cost or range, something that I think we're all looking forward to.
The reason I asked Pete to do just a detail, far more detailed than perhaps most people would appreciate, dive into the Tesla full self-driving computer is because at first it seems improbable. How could it be that Tesla, who has never designed a chip before, would design the best chip in the world? But that is objectively what has occurred. Not best by a small margin, best by a huge margin. It's in the cars right now. All Teslas being produced right now have this computer. We switched over from the Nvidia solution for S and X about a month ago, and we switched over Model 3 about 10 days ago. All cars being produced have all the hardware necessary, compute and otherwise, for full self-driving. I'll say that again. All Tesla cars being produced right now have everything necessary for full self-driving. All you need to do is improve the software. And later today, you will drive the cars with the development version of the improved software, and you will see for yourselves. questions for Pete?
Yeah.
So, you talked about the software as the piece now. You did a great job. I was blown away. Understood 10% of what you said, but I trust that it's in good hands. So maybe on the chip side, the last slide was 144 trillions of operations per second versus, was it Nvidia at 21?
That's right.
And maybe can you just contextualize that for a finance person, why that's so significant, that gap? Thank you.
Well, I mean, it's a factor of 7 in performance delta, so that means you can do 7 times as many frames. You can run neural networks that are 7 times larger and more sophisticated. So it's a very big currency that you can spend on lots of interesting things to make the car better.
I think that Xavier power usage is higher than ours. I believe it's like power increased at least to the same degree, a factor of 7, and costs would also increase by a factor of 7. And power is a real problem because it also reduces range. The thermal problem becomes really significant because you've got to get rid of all that power. To be clear, like the strategy here, and this started basically a little over 3 years ago, was design and build a computer that is fully optimized and aiming for full self-driving, and write software that is designed to work specifically on that computer and get the most out of that computer. That is a master of one trade, self-driving. And Nvidia is a great company, but they have many customers. And so as by their resources, they need to do a generalized solution. We care about one thing, self-driving. Software is also designed to run on that hardware incredibly well. And the combination of the software and the hardware, I think, is unbeatable.
The chip is designed to process video input. In case you use, let's say, Lidar, would it be able to process that as well, primarily for video?
What we're going to explain to you today is that Lidar is a fool's errand. And anyone relying on Lidar is doomed. Doomed. Expensive sensors that are unnecessary. It's like having a whole bunch of expensive appendices. Like one appendix is bad, well, now we're put a whole bunch of them. That's ridiculous. You'll see.
Graham Tanaka Capital. Just curious how defensible your chip technologies and design is. You won't be offering a lot of the IP to the outside for free. Thanks.
We have filed on the order of 12 patents.
I think if somebody started today and they were really good, they might have something like what we have right now in 3 years. But in 2 years, we'll have something 3 times better. We do encrypt it's a hard chip to crack.
It's our intention to prevent people from stealing all that stuff. I mean, if they do, we hope it at least takes a long time.
It will definitely take them a long time. The thing that's, I think, a very powerful, sustainable advantage for us is the fleet. Nobody has the fleet. Those weights are constantly being updated and improved based on billions of miles driven. Tesla has 100 times more cars with the full self-driving hardware than everyone else combined. Some of them will still be on hardware too, but we still have the data gathering ability. And then by a year from now, we'll have over 1 million cars with full self-driving computer, hardware, everything. Just a massive data advantage. It's similar to how the Google search engine has a massive advantage because people use it. And people are effectively programming Google with their queries and the results.
When we talk to Waymo or Nvidia, they do speak with equivalent conviction about their leadership because of their competence in simulating miles driven. Can you talk about the advantage of having real-world miles versus simulated miles?
Absolutely. We have quite a good simulation too, but it just does not capture the long tail of weird things that happen in the real world. If the simulation fully captured the real world, well, that would be proof that we're living in a simulation, I think. It doesn't. I wish. But simulations do not capture the real world. The real world's really weird and messy. You need the cars on the road. So, okay, why don't we move on to Andre?
Great. Thank you. Thank you, everybody. Thank you very much.
Andre started the computer vision class at Stanford. That's much more significant. That's what matters. So, can you please talk about your background?
I think I've been training neural networks basically for what is now a decade, and that included institutions at Stanford, at OpenAI, at Google. Really just training a lot of neural networks, not just for images, but also for natural language. So Pete told you all about the chip that we've designed that runs neural networks in the car. My team is responsible for training of these neural networks, and that includes all of data collection from the fleet, neural network training, and then some of the deployment onto that chip. What do the neural networks do exactly in the car? So what we are seeing here is a stream of videos from across the vehicle, across the car. These are 8 cameras that send out videos, and then these neural networks are looking at those videos and are processing them and making predictions about what they're seeing. And so some of the things that we're interested in and some of the things you're seeing on this visualization here are lane line markings, other objects, the distances to those objects, what we call drivable space, shown in blue, which is where the car is allowed to go, and a lot of other predictions like traffic lights, traffic signs, and so on. For my talk, I will talk roughly in 3 stages. So first, I'm going to give you a short primer on neural networks and how they work and how they're trained. And I need to do this because I need to explain in the second part why it is such a big deal that we have the fleet and why it's so important, and why it's a key enabling factor to really training these neural networks and making them work effectively on the roads. So the core problem that these networks are solving in the car is that of visual recognition. So for you and I, this is a very simple problem. You can look at all of these 4 images and you can see that they contain a cello, a boat, an iguana, or scissors. So this is very simple and effortless for us. This is not the case for computers. And the reason for that is that these images are, to a computer, really just a massive grid of pixels. And at each pixel, you have the brightness value at that point. And so instead of just seeing an image, a computer really gets a million numbers in a grid that tell you the brightness values at all the positions.
The matrix, if you will. It really is the matrix.
Yeah. And so we have to go from that grid of pixels and brightness values into high-level concepts like iguana and so on. And as you might imagine, this iguana has a certain pattern of brightness values, but iguanas actually can take on many appearances. So they can be in many different appearances, different poses, and different brightness conditions against different backgrounds. You can have different crops of that iguana. And so we have to be robust across all those conditions, and we have to understand that all those different brightness patterns actually correspond to iguanas. Now, the reason you and I are very good at this is because we have a massive neural network inside our heads that is processing those images. So light hits the retina, travels to the back of your brain to the visual cortex, and the visual cortex consists of many neurons that are wired together and that are doing all the pattern recognition on top of those images. And really, over the last, I would say about 5 years, the state-of-the-art approaches to processing images using computers have also started to use neural networks, but in this case, artificial neural networks. But these artificial neural networks, and this is just a cartoon diagram of it, are a very rough mathematical approximation to your visual cortex. We really do have neurons, and they are connected together. And here I'm only showing 3 or 4 neurons in 4 layers, but a typical neural network will have tens to hundreds of millions of neurons, and each neuron will have 1,000 connections. So these are really large pieces of almost simulated tissue. And then what we can do is we can take those neural networks and we can show them images. So for example, I can feed my iguana into this neural network, and the network will make predictions about what it's seeing. Now, in the beginning, these neural networks are initialized completely randomly. So the connection strengths between all those different neurons are completely random. And therefore, the predictions of that network are also going to be completely random. So it might think that you're actually looking at a boat right now, and it's very unlikely that this is actually an iguana. And during the training process, really what we're doing is we know that that's actually an iguana. We have a label. So what we're doing is we're basically saying we'd like the probability of iguana to be larger for this image and the probability of all the other things to go down. And then there's a mathematical process called backpropagation and stochastic gradient descent that allows us to backpropagate that signal through those connections and update every one of those connections, just a little amount. And once the update is complete, the probability of iguana for this image will go up a little bit, so it might become 14%, and the probability of the other things will go down. And of course, we don't just do this for this single image. We actually have entire large data sets that are labeled. So we have lots of images. Typically, you might have millions of images, thousands of labels, or something like that. And you are doing forward-backward passes over and over again. So you're showing the computer, here's an image, it has an opinion, and then you're saying this is the correct answer, and it tunes itself a little bit. You repeat this millions of times. And sometimes you show images, the same image to the computer, hundreds of times as well. So the network training typically will take on the order of a few hours or a few days, depending on how big of a network you're training. And that's the process of training a neural network. When it comes to training data for neural networks, there really is no substitute for real data. The simulations have a lot of trouble with modeling appearance, physics, and the behaviors of all the agents around you. So there are some examples to really drive that point across. The real world really throws a lot of crazy stuff at you. So in this case, for example, we have very complicated environments with snow, with trees, with wind. We have various visual artifacts that are hard to simulate potentially. We have complicated construction sites, bushes, and plastic bags that can go in, go around with the wind. Complicated construction sites that might feature lots of people, kids, animals, all mixed in, and simulating how those things interact and flow through this construction zone might actually be completely intractable. It's not about the movement of any one pedestrian in there. It's about how they respond to each other and how those cars respond to each other and how they respond to you driving in that setting. And all of those are actually really tricky to simulate. It's almost like you have to solve the self-driving problem to just simulate other cars in your simulation. So it's really complicated. So we have dogs, exotic animals, and in some cases, it's not even that you can't simulate it, it's that you can't even come up with it.
Simulation, you're fundamentally grading your own homework. So if you know that you're going to simulate it, okay, you can definitely solve for it. But as Andre is saying, you don't know what you don't know. The world is very weird and has millions of corner cases. And if somebody can produce a self-driving simulation that accurately matches reality, that in itself would be a monumental achievement of human capability. They can't. There's no way.
I think the 3 points that I really tried to drive home until now are, to get neural networks to work well, you require these 3 essentials. You require a large data set, a varied data set, and a real data set. And if you have those capabilities, you can actually train neural networks and make them work very well. So why is Tesla in such a unique and interesting position to really get all these 3 essentials right? And the answer to that, of course, is the fleet. We can really source data from it and make our neural network systems work extremely well. So let me take you through a concrete. So to summarize, the process by which we iterate on neural network predictions looks something like this. We start with a seed data set that was potentially sourced at random. We annotate that data set, and then we train neural networks on that data set and put that in the car. And then we have mechanisms by which we notice inaccuracies in the car when this detector may be misbehaving. So for example, if we detect that the neural network might be uncertain, or if we detect that, or if there's a driver intervention on any of those settings, we can create this trigger infrastructure that sends us data of those inaccuracies. And so for example, if we don't perform very well on lane line detection on tunnels, then we can notice that there's a problem in tunnels. That image would enter our unit tests so we can verify that we're actually fixing the problem over time. But now what you do is, to fix this inaccuracy, you need to source many more examples that look like that. So we ask the fleet to please send us many more tunnels, and then we label all those tunnels correctly. We incorporate that into the training set, and we retrain the network, redeploy, and iterate the cycle over and over again. And so we refer to this iterative process by which we improve these predictions as the data engine. So iteratively deploying something, potentially in shadow mode, sourcing inaccuracies and incorporating them into the training set over and over again. And we do this basically for all the predictions of these neural networks. So what I want to talk about also is really to utilize the power of the fleet. You don't want to go through this human annotation bottleneck. You want to just stream in data and automate it automatically. And we have multiple mechanisms by which we can do this. So as one example of a project that we recently worked on is the detection of cut-ins. So you're driving down the highway, someone is on the left or on the right, and they cut in front of you into your lane. So here's a video showing the autopilot detecting that this car is intruding into our lane. Now, of course, we'd like to detect a cut-in as fast as possible. So the way we approach this problem is we don't write explicit code for, is the left blinker on, is the right blinker on, track the cuboid over time and see if it's moving horizontally. We actually use a fleet learning approach. So the way this works is we ask the fleet to please send us data whenever they see a car transition from a right lane to the center lane, or from left to center. And then what we do is we rewind time backwards, and we automatically can annotate that, hey, that car will in 1.3 seconds cut in front of you. And then we can use that for training the neural net. And so the neural net will automatically pick up on a lot of these patterns. So for example, the cars are typically yawed, they're moving this way, maybe the blinker is on. All that stuff happens internally inside the neural net just from these examples. So we ask the fleet to automatically send us all this data. We can get 500,000 or so images, and all of these would be annotated for cut-ins, and then we train the network. And then we took this cut-in network and we deployed it to the fleet, but we don't turn it on yet. We run it in shadow mode. And in shadow mode, the network is always making predictions. Hey, I think this vehicle is going to cut in from the way it looks. This vehicle is going to cut in. And then we look for mispredictions. So as an example, this is a clip that we had from shadow mode of the cut-in network. And it's kind of hard to see, but the network thought that the vehicle right ahead of us on the right was going to cut in. And you can sort of see that it's slightly flirting with the lane line. It's sort of encroaching a little bit. And the network got excited and it thought that was going to be cut in. That vehicle will actually end up in our center lane. That turns out to be incorrect, and the vehicle did not actually do that. So what we do now is we just churn the data engine. We source That ran in the shadow mode is making predictions. It makes some false positives, and there are some false negative detections. So we got overexcited and sometimes we missed a cut-in when it actually happened. All those create a trigger that streams to us, and that gets incorporated now for free. There's no humans harmed in the process of labeling this data. Incorporated for free into our training set. We retrain the network and redeploy the shadow mode. And so we can spin this a few times, and we always look at the false positives and negatives coming from the fleet. And once we're happy with the false positive, false negative ratio, we actually flip the bit and actually let the car control to that network. And so you may have noticed, we actually shipped one of our first versions of a cut-in detector approximately, I think, 3 months ago. So if you've noticed that the car is much better at detecting cut-ins, that's fleet learning operating at scale. So that's fleet learning. No humans were harmed in the process. It's just a lot of neural network training based on data and a lot of shadow mode and looking at those results.
Essentially, like everyone's training the network all the time is what it amounts to. Whether autopilot is on or off, the network is being trained. Every mile that's driven for the car that's hardware 2 or above is training the network.
Yeah. So here's an example of path prediction going through a kind of a complicated environment. So what you're seeing here is a video, and we are overlaying the predictions of the network. So this is a path that the network would follow in green. And
the crazy thing is, the network is predicting paths it can't even see with incredibly high accuracy. It can't see around the corner, but it's saying the probability of that curve is extremely high. So that's the path, and it nails it. You'll see that in the cars today. We're going to turn on augmented vision, so you can see the lane lines and the path predictions of the cars overlaid on the video. I mean, it's kind of scary, to be honest. Yeah.
And of course, there's a lot of details I'm skipping over. You might not want to annotate all the drivers. You might want to just imitate the better drivers. And there's many technical ways that we actually slice and dice that data prediction that we project back to the image here. So the path here forward is a 3-dimensional thing that we're just rendering in 2D. But we know about the slope of the ground from all this, and that's actually extremely valuable for driving. So path prediction actually is live in the fleet today, by the way. So if you're driving cloverleafs, if you're in a cloverleaf on the highway, until maybe 5 months ago or so, your car would not be able to do cloverleaf. Now it can. That's path prediction running live on your cars. We've shipped this a while ago. And today you are going to get to experience this for traversing intersections. A large component of how we go through intersections in your drives today is all sourced from path prediction from automatic labels. What I talked about so far is really the 3 key components of how we iterate on the predictions of the network and how we make it work over time. You require large, varied, and real data set. We can really achieve that here at Tesla. And we do that through the scale of the fleet, the data engine, shipping things in shadow mode, iterating that cycle, and potentially even using fleet learning where no human annotators are harmed in the process, and just using data automatically, and we can really do that at scale. The other project that I want to briefly talk about is, as I mentioned, there's nothing about neural network. Neural networks are very powerful visual recognition engines, and if you want them to predict depth, then you need to, for example, look for labels of depth, and then they can actually do that extremely well. So there's nothing limiting networks from predicting this molecular depth except for labeled data. So one example project that we've actually looked at internally is we use the forward-facing radar, which is shown in blue, and that radar is looking out and measuring depths of objects, and we use that radar to annotate the what vision is seeing, the bounding boxes that come out of the neural networks. So instead of human annotators telling you, okay, this car and this bounding box is roughly 25 meters away, you can annotate that data much better using sensors. So you use sensor annotation. So as an example, radar is quite good at that distance. You can annotate that, and then you can train a neural network on it. And if you just have enough data of it, this neural network is very good at predicting those patterns. So here's an example of predictions of that. So in circles, I'm showing radar objects, and the cuboids that are coming out of here are purely from vision. So in summary, people drive with vision only. No lasers are involved. This seems to work quite well. The point that I'd like to make is that visual recognition, very powerful visual recognition, is absolutely necessary for autonomy. It's not a nice to have. Like, we must have neural networks that actually really understand the environment around you. And LiDAR points are a much less information-rich environment. So vision really understands the full details. Just a few points around are much, there's much less information in those. The entire infrastructure that we have built up for roads is all designed for human visual consumption. So all the signs, all the traffic lights, everything is designed for vision. And so that's where all that information is. And so you need that ability. Is that person distracted and on their phone? Are they going to walk into your lane? Those answers to all these questions are only found in vision, are necessary for level 4, level 5 autonomy. And that is the capability that we are developing at Tesla. And this is done through combination of large-scale neural network training, through data engine, getting that to work over time, and using power of the fleet. And so in this sense, LiDAR is really a shortcut. And so it gives a false sense of progress and is ultimately a crutch. So if I was to summarize the entire, my entire talk in one slide, it would be this. All of autonomy, because you want level 4, level 5 systems that can handle all the possible situations in 99.99% of the cases. And chasing some of the last few nines is going to be very tricky and very difficult, and is going to require a very powerful visual system. So I'm showing you some images of what you might encounter in any one slice of that 9. So in the beginning, you just have very simple cars going forward. Then those cars start to look a little bit funny. Then maybe you have bikes on cars. Then maybe you have cars on cars. Then maybe you start to get into really rare events like cars turned over, or even cars airborne. We see a lot of things coming from the fleet. And we see them at some rate, at like a really good rate compared to all of our competitors. And so the rate of progress at which you can actually address these problems, iterate on the software, and really feed the neural networks with the right data, that rate of progress is really just proportional to how often you encounter these situations in the wild. And we encounter them significantly more frequently than anyone else, which is why we're going to do extremely well. Thank you.
But the one challenge that I'm curious to how you're going to solve is changing lanes. Because whenever I try to get into a lane with traffic, everybody cuts you off. And so human behavior is very irrational when you're driving in LA, and the car just wants to do it safely, and you almost have to do it unsafely. So I was wondering how you're going to solve that problem.
Probably have a mode that goes beyond Mad Max mode to LA traffic mode. Yeah. Well, Mad Max would have a hard time in LA traffic, I think.
Yeah, so really it's a trade-off. Like, you don't want to create unsafe situations, but you want to be assertive. But that little dance of how you make that work as a human is actually very complicated. It's very hard to write in code.
We're just being more conservative right now, and then as we gain higher and higher confidence, we'll allow users to select a more aggressive mode. That'll be up to the user. In the more aggressive modes, in trying to merge in traffic, there is a slight, no matter how many use, there's a slight chance of a fender bender, not a serious accident, but you basically will have a choice of, do you want to have a non-zero chance of a fender bender on freeway traffic, which is unfortunately the only way to navigate LA traffic.
Hi, Jed Dorsheimer from Canaccord Genuity. Thank you and congratulations on everything that you've developed. What you're trying to do here is almost develop consciousness in the cars through the neural network. And so I guess the challenge is, how do you not create a circular reference? Car has enough information, the point of the learning process to handing it off, where there's enough information in the car and not having to pull from the fleet.
Well, the car can operate if it's completely disconnected from the fleet. It uploads the training that's better and better as the fleet gets better and better. So simply, if you disconnected it from the fleet, from that point onwards, it would stop getting better, but it would still function fine. I mean, the compute power in the full self-driving computer is incredible, and maybe we should. If it had never seen that road before, it would still have made those predictions, provided it was a road in the United States.
In the case of LiDAR, the March of Nines, isn't there an example? I want to just get to your slam on LiDAR, because it was pretty clear you don't like LiDAR. And this
LiDAR is lame. LiDAR is lame.
That isn't there a case where at some point 99999 down the road, where actually LiDAR may be helpful, and why not have it as some sort of a redundancy or backup? So that's my first question. And the second, so you can still have your focus on computer vision, but just have it as a redundant. And my second question is, if that is true, what happens to the rest of the industry that's building their autonomy solutions on LiDAR?
They're all going to dump LiDAR, is my prediction. Mark my words. I should point out that I don't actually super hate LiDAR as much as it may sound, but at SpaceX, SpaceX Dragon uses LiDAR to navigate to the space station and dock. Not only that, SpaceX developed its own LiDAR from scratch to do that, and I spearheaded that effort personally, because in that scenario, LiDAR makes sense, and in cars, it's freaking stupid. It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless. So you have expensive hardware that's worthless on the car. We do have a forward radar, which is low cost and is helpful, especially for occlusion situations. So if there's fog or dust or snow, the radar can see through that. if you're going to use active photon generation, don't use visible wavelength, because once with passive optical, you've taken care of all visible wavelength stuff. You want to, if you want to use a wavelength that is occlusion penetrating, like radar. So LiDAR is just active photon generation in the visual spectrum, 8 cameras and the forward radar. You only need the radar in the forward direction because that's the only direction you're going real fast. So I mean, we've gone over this multiple times. Like, are we sure we have the right sensor suite? Should we add anything more? No.
That you ask the fleet for the information that you're looking for some of the vision. I have 2 questions about that. It sounds like the cars are doing some computation to determine what kind of information to send back to you. Is that a correct assumption? And are they doing that in real time, or are they doing
on the car? And we will wait to basically specify condition that we're interested in. And then those cars do that computation there. If they did not, then we'd have to send all the data and do that offline in our backend. We don't want to do that. So all that computation happens on the car.
So it's based on that question, it sounds like you guys are in a really good position to have currently 500,000 cars, in the future potentially millions of cars that are essentially computers representing future opportunity for Tesla.
Current
opportunity, and that's not really factored in for anything yet. That's incredible. Thank you.
We have 425,000 cars with hardware 2 and beyond, which means they've got all 8 cameras, the radar, and the ultrasonics. And they've got at least the Nvidia computer, which is enough to essentially figure out what information is important, what is not, compress the information that is important to the most salient elements, and upload it to the network for training. So it's a massive compression of real-world data.
Hi, Elon. Matt Joyce, Loop Ventures. I own a Model 3 in Minnesota where it snows a lot. Since camera and radar cannot see road markings through snow, what is your technical strategy to solve this challenge? Does it involve high precision GPS at all?
Actually, like today, Autopilot will do a decent job in snow, even when lane markings are covered. Even when lane markings are faded, covered, or when there's lots of rain on them, we still seem to drive relatively well. We didn't specifically go after snow yet with our data engine, but I actually think this is completely tractable, because in a lot of those images, even when things are snowy, when you ask a human annotator where are the lane lines, they actually could tell you. They actually are relatively consistent in creating those lane lines. As long as the annotators are consistent on your data, then the neural network will pick up on those patterns and will do just fine. So it's really just about, is the signal there even for the human annotator? If the answer to that is yes, then the neural network can do it just fine.
Yeah, there's actually there are a number of important signals, as Andre was saying. So lane lines are one of those things, but one of the most important signals is drive space. So what is drivable space and what is not drivable space? And what actually really matters the most is drivable space more than lane lines. And the prediction of drivable space is extremely good. And I think especially after this upcoming winter will be incredible. It's like, it will be like, how could it possibly be that good? That's crazy. Yeah.
The other thing to point out is maybe it's not even only about human annotators. As long as you as a human can drive through that environment, exactly. Through fleet learning, we actually know the path you took. Mm-hmm. And you obviously use vision to guide you through that path. You did not just use the lane line markings. You used the entire geometry of that entire scene. So you see, you see how the road is roughly curling. You see how the cars are positioned around you. Neural network will pick up on all of those patterns automatically inside it if you just have enough of the data, people traversing those environments.
Yeah, it's actually extremely important that things not be rigidly tied to GPS, because GPS error can vary quite a bit, and the actual situation for a road can vary quite a bit. So there could be construction, there could be a detour, and if the car is using GPS as primary, this is a real bad situation. It's asking for trouble. It's fine to use GPS for like tips and tricks. So it's like you can drive your home neighborhood better than a neighborhood in like some other country or some other part of the country. So you know your own neighborhood well, and you use kind of like the knowledge of your neighborhood to drive with more confidence, to maybe have counterintuitive shortcuts and that kind of thing. But the GPS overlay data should only be helpful but never primary. If it's ever primary, it's a problem.
So, question back here in the back corner. I just wanted to follow up partially on that because several of your competitors in the space over the past few years have made, have talked about how they are augmenting all of their perception and path planning capabilities that are kind of on the car platform with high definition maps of the areas that they are driving. Does that play a role in your system? Do you see it adding any value? Are there areas where you would like to get more data that is not collected from the fleet, but is more kind of mapping style data?
I think the high precision GPS maps and lanes are a really bad idea. The system becomes extremely brittle. So any change, like any change to the system makes it can't adapt. So if it locks onto GPS and high precision lane lines, and does not allow a vision override. In fact, vision should be the thing that does everything, and then like lane lines are a guideline, but they're not the main thing. We briefly balked up the tree of high precision lane lines, and then realized that was a huge mistake, and reversed it out. It's not good.
So this is very helpful for understanding annotation, where the objects are and how the car drives, but what about the negotiation aspect for parking and roundabouts and other things where there are other cars on the road that are human driven, where it's more art than science?
It does pretty good, actually. Like with cut-ins and stuff, it's doing really well.
So like I mentioned, we're using a lot of machine learning right now in terms of predicting, kind of creating an explicit representation of what the road looks like, and then there's an explicit planner and a controller on top of that representation, and there's a lot of heuristics for how to traverse and negotiate and so on. There is a long tail, just like in what visual environments look like, there's a long tail in just those negotiations and a little game of chicken that you play with other people and so on. And so I think we have a lot of confidence that eventually there must be some kind of a fleet learning component to how you actually do that, because writing all those rules by hand is going to quickly plateau, I think.
Yeah, we've dealt with this issue with cut-ins, and it's like we'll allow gradually more aggressive behavior on the part of the user. You can just dial the setting up and say, be more aggressive, be less aggressive, drive easy, chill mode, aggressive. Yeah.
Incredible progress, phenomenal. Two questions. First, in terms of platooning, do you think the system is geared? Because somebody asked about when there is snow on the road, but if you have platooning feature, you can just follow the car in front. Is your system capable of doing that? Then I have two follow-ups.
So you're asking about platooning. So I think like we could absolutely build those features, but again, if you just train neural networks, for example, on imitating humans already follow the car ahead, and so that neural network actually incorporates those patterns internally. It figures out that there's a correlation between the way the car ahead of you faces and the path that you are going to take. But that's all done internally in the net. So you're just concerned with getting enough data and the tricky data, and the neural network training process actually is quite magical. Does all the other stuff automatically. So you turn all the different problems into just the one problem. Just collect your data set and use neural network training.
Yeah, there's three steps to self-driving. There's being feature complete. Then there's being feature complete to the degree that where we think that the person in the car does not need to pay attention. And then there's being at a reliability level where we've also convinced regulators that is true. So there's kind of like three levels. We expect to be feature complete in self-driving this year, and we expect to be confident enough from our standpoint to say that we think people do not need to touch the wheel, look out of the window, sometime probably around, second quarter of next year. And then we expect to get regulatory approval, at least in some jurisdictions, for that towards the end of next year. That's roughly the timeline that I expect things to go on. And probably for trucks, the platooning will be approved by regulators before anything else.
Yeah, I've been actually very impressed by the rate of improvement on autopilot the past year on my Model 3. The two scenarios I wanted your feedback on. Last week, the first scenario was I was on the right hand, most lane of the freeway, and there was a highway on-ramp. And then my Model 3 actually was able to detect the two cars on the side, slow down and let the car go in front of me and one car go behind me. And I was like, oh my gosh, this is like insane. Like I didn't think my Model 3 could do that. So that was like super impressive. But the same week, another scenario, which is I was on the right-hand lane again, but my right-hand lane was merging with the left lane. And it wasn't an on-ramp, it's just a normal freeway lane. And my Model 3 wasn't able to detect really that situation, and I wasn't able to slow down or speed up, and I had to intervene, kind of. So can you, from your perspective, kind of share kind of the background on how a neural net would, how Tesla might adjust for that, and like how that could be improved over time?
Yeah. So like I mentioned, we have a very sophisticated trigger infrastructure. If you have intervened, it's actually potentially likely that we receive that clip and that we can actually analyze it and see what happened and tune the system. So it probably enters some statistics over, okay, at what rate are we correctly merging the traffic? And we look at those numbers and we look at the clips and we see what's wrong and we try to fix those clips and make progress against those benchmarks. So we would potentially go through a phase of categorization, and then we look at some of the biggest categories that actually seem to semantically be related to to the same problem, and then we would look at some of those, and then try to develop software against that.
Okay, we do have one more presentation, which is the software. So it's like essentially the autopilot hardware with Stuart. There's the sort of neural net vision with Andre, and then there's the software engineering at scale that's going to be presented by Stuart. So thanks, and we'll have an opportunity afterwards to ask questions. So yeah, thanks.
So I'm Stuart, and I'm here to talk about how we build some of these systems at scale. Just like a really short introduction on kind of where I'm coming from, what I do. So I've been in a couple companies where I've been writing software professional for about 12 years. The thing that excites me most and I'm really passionate about is taking the cutting edge of machine learning and actually connecting that with customers to robustness and scale. So at Facebook, I worked initially inside of our ads infrastructure to build some of the machine learning for really, really smart people. We actually tried to build that to a single platform that we could then scale to all the other aspects of the business, from how we rank the newsfeed, to how we deliver search results, to how we make every recommendation across the platform. And that became the Applied Machine Learning Group. That's something I'm incredibly proud of. And a lot of that wasn't just the core algorithms and the really important improvements that happen there, because that matters. A lot of it actually the engineering practices to build these systems at scale. And the same thing was true at Snap, where 70 million miles already for Navigate on autopilot is something really, really cool. And I think one thing that is worth kind of calling out on this is that we're continuing to accelerate and keep learning from this data. Like Andre talked about this data engine, as this accelerates up, we actually do make more and more assertive lane changes. We are learning from these cases where people intervene, either because they failed to detect a merge correctly, or because they wanted the car to be a little more peppy in different environments, and we just want to keep making that progress. So to start all of this, we begin with trying to understand the world around us. And we talked about the different sensors in the vehicle, but I want to dig in a little bit more here. We have 8 cameras, but then we also have additionally 12 ultrasonic sensors, a radar, an inertial measurement unit, GPS, and then one thing we forget about is we also have the pedal and steering actions. So not only can we look at what's happening around the vehicle, we can look at how humans chose to interact with that environment. And so I'll talk to this clip right now. This basically is showing what's happening today in the car, and we're continuing to push this forward. So we start with a single neural network. We see the detections around it. We then build all that together with multiple neural networks and multiple detections. We bring in the other sensors, and we convert that into what Elon calls a vector space, an understanding of the world around us. And this is something where, as we continue to get better and better at this, we're moving more and more of this logic into the neural networks themselves. And the obvious end game here is that the neural network looks across all the cars, brings in all the information together, and just ultimately outputs a source of truth for the world around us. And this is actually not like an artist rendering in many senses. This is actually the output of one of the debugging tools that we use on the team every day to understand what the world looks like around us. So another thing that I think is really, really exciting to me, I think when I do hear about sensors like LiDAR, a common question is around just having extra sensor modalities. Like, why not have some redundancy on the vehicle? And I want to dig in on one thing that's not always obvious with neural networks themselves. So we have a neural network running on our, say, wide fisheye camera. That neural network is not making one prediction about the world. It's making many separate predictions, some of which actually audit each other. So as a real example, we have the ability to detect a pedestrian. That's something we train very, very carefully on and put a lot of work into. We also have the ability to detect obstacles in the roadway, and a pedestrian is an obstacle. And it's shown differently to the neural network. It says, oh, there's a thing I can't drive through. And these together combine to give us an increased sense of what we can and can't do in front of the vehicle and how to plan for that. We then do this across multiple cameras because we have overlapping fields of view in many places around the vehicle. In front, we have a particularly large number of overlapping fields of view. Lastly, we can combine that with things like the radar and the ultrasonics to build these extremely precise understandings of what's happening in front of the car. We can use that both to learn future behaviors that are very accurate. We can also build very accurate predictions of how things will continue to happen in front of us. So one example I think is really exciting is we can actually look at bicyclists and people and not just ask, where are you now, but where are you going? And this is actually the heart of what we're doing for our next generation automatic emergency braking system, which will not just stop for people in your path, it will stop for people who are going to be in your path. And that's running in shadow mode right now. We'll go out to the fleet this quarter, and I'll talk about shadow mode in a second. So when you want to start a feature like this for navigating on autopilot on the highway system, you can start by learning from data, and you can just look at how humans do things today. What is their assertiveness profile? How do they change lanes? What causes them to either abort or change it, like their maneuvers? And you can see things that are not immediately obvious, like, oh yeah, simultaneous merging is rare, but very complicated and very important. And you can start to build opinions about different scenarios, such as a fast overtaking vehicle. So this is what we do when we initially have some algorithms we want to try out. We can put them on the fleet, and we can see what they would have done in a real-world scenario, such as this car that's overtaking us very quickly. And this is taken from our actual simulation environment, showing different paths that we have considered taking and how those overlay on the real world of, in this case, I think a really fun example, like these very interesting cases of simultaneous merging where you start going and then somebody moves either behind or before you, not noticing you. And what is the appropriate behavior here? And what are the tunings of the neural network we need to do to be super precise about the appropriate behaviors here? We tuned these in the background, we made them better, and we got 9 million successfully accepted lane changes. And so earlier this month, we're ready to deploy an even more seamless version of Navigate on Autopilot on the highway system. And that seamless version does not require a stock confirm. So you can sit there, relax, put your hand on the wheel, and just oversee what the car is doing. And in this case, we're actually seeing over 100,000 automated lane changes every single day on the highway system. And this is something that's just like super cool to us to deploy at scale. And the thing that I'm kind of most excited about from all this is the actual life cycle of this and how we actually are able to turn that data engine crank faster and faster and faster with time. And I think one combination of the infrastructure we have built, the tooling we built on top of that, and the combined power of the full self-driving computer, I believe we can do this even faster as we move Navigate on Autopilot from the highway system onto city streets. And so, yeah, with that, I'll hand off to you.
To the best of my knowledge, all those lane changes have occurred with 0 accidents.
That is correct. Yeah, I watch every single accident. So,
yeah. So it's conservative, obviously, but it's have hundreds of thousands going to millions of lane changes and 0 accidents is I think a great achievement by the team.
Thank you.
Cool. In order to have a self-driving car or robo-taxi, you really need redundancy throughout the vehicle at the hardware level. So starting in, I believe it was October 2016, all cars made by Tesla have redundant power steering. So redundant motors in the power steering. So any one failure of if the motor fails, the car can still steer. All of the power and data lines have redundancy. So you can sever any given power line or any data line and the car will keep driving. The auxiliary power system, even if the main pack, you lose complete power in the main pack, the car is capable of steering and braking using the auxiliary power system. You can completely lose the main pack and the car is safe. The whole system, from a hardware standpoint, has been designed to be a robo-taxi since basically October 2016. So when we rolled out hardware, Autopilot version 2. But we do not expect to upgrade cars made before that. We think it would actually cost more to make a new car than to upgrade the cars. Just to give you a sense of how hard it is to do this. Unless it's designed in, it's not worth it. So we've gone through the future of self-driving, where it's clear it's hardware, it's vision, And then there's a lot of software, and there's the software problem here should not be minimized. It's a massive software problem managing vast amounts of data, training against the data, how do you control the car based on the vision? It's a very difficult software problem. So going over just like Tesla master plan, obviously we've made a bunch of forward-looking statements, as they call it. But let's go through some of our other forward-looking statements that we've made. Way back when we created the company, we said we'd build the Tesla Roadster. They said it was impossible, and that even if we did build it, nobody would buy it. It was like universal opinion was that building an electric car was extremely dumb and would fail. I agree with them that probability of failure was high, but that was important. So, going to production in 2008 and shipping that car, it's now a collector's item. Then so we built a more affordable car with the Model S. We did that. Again, we were told that's impossible. I was called a fraud and a liar. It was not going to happen. It was all untrue. Okay, famous last words. Now we went to production with the Model S in 2012. It exceeded all expectations. There is still, in 2019, no car that can compete with Model S of 2012. It's 7 years later. Still waiting. So we built an affordable car, maybe highly affordable. It's affordable, more affordable with Model 3. We built the Model 3. We're in production. So we'd get over 5,000 cars a week for Model 3. At this point, 5,000 cars a week is a walk in the park for us. It's not even hard. So we do large-scale solar, which we did through the Solar City acquisition, and that we developed and deployed Solar Roof, which is going really well. We're now on version 3 of the solar tile roof, and we expect to scale up production of the solar tile roof significantly later this year. I have it on my house, and it's great. And I said we make the power wall and the power pack. We made the power wall and power pack. In fact, the power pack is now deployed in massive grid-scale utility systems around the world, including the largest operating battery projects in the world that above 100 megawatts. And in the next, or probably by next year, 2 years at the most, we expect to have a gigawatt scale battery project completed. So all these things, I said we'd do them, we did it. So we'd do it, we did it. We're going to do the Robo-taxi thing too. Only criticism, and it's a fair one, and sometimes I'm not on time. But I get it done. And the Tesla team gets it done. So what we're going to do this year is we're going to reach combined production of 10,000 a week between S6 and 3. Feel very confident about that. And we feel very confident about being feature complete with self-driving. Next year, we'll expand the product line with Model Y and Semi, and we expect to have the first operating robo-taxis next year, with no one in them next year. It's always difficult to, like, when things are on an exponential, at an exponential rate of improvement, it's very difficult to kind of wrap one's mind around it because we're used to extrapolating on a linear basis. But when you've got massive amounts of like, as the hardware, massive amounts of hardware on the road, the cumulative data is increasing exponentially. The software is getting better at an exponential rate. I feel very confident predicting autonomous robo-taxis for Tesla next year. Not in all jurisdictions because we won't have regulatory approval everywhere, but I'm confident we'll have at least regulatory approval somewhere literally next year. So any customer will be able to add or remove their car to the Tesla network. So we expect this to operate is sort of like a combination of maybe the Uber and Airbnb model. So if you own the car, you can add or subtract it to the Tesla network, and Tesla would take and 25 or 30% of the revenue. And then in places where there aren't enough people sharing their cars, we would just have dedicated Tesla vehicles. So when you use the car, we'll show you our ride-sharing app. So you're able to summon the car from the parking lot, get in, and go for a drive. It's really simple. You just take the same Tesla app that you currently have, we'll update the app and add a summon Tesla or commit your car to the fleet. So it's either summon your car or summon a Tesla or add or subtract your car to the fleet. You'll be able to do that from your phone. So we see potential for smoothing out the demand distribution curve and having the car operate at a much higher utility than a normal car operates. So, like typically, the use of a car is about 10 to 12 hours a week. So most people will drive 1.5 to 2 hours a day, typically 10 to 12 hours a week of total driving. But if you have a car that can operate autonomously, then most likely you'd have that car operate for a third of the week or longer. So there are 168 hours in a week, so probably you've got something on the order of 55 to 60 hours a week of operation, maybe a bit longer. So the fundamental utility of the vehicle increases by a factor of 5. So you look at this from a macroeconomic standpoint and say, just if this was like if we were operating some big simulation, if you could upgrade your simulation to increase the utility of cars by a factor of 5, that would be a massive increase in the economic efficiency of the simulation. Just gigantic. So we'll do Model 3, S3 and X's taxis, but we made an important change to our leases. So if you lease a Model 3, you don't have the option of buying it at the end of the lease. We want them back. If you buy the car, you can keep it. If you lease it, you have to give it back. And as I said, where in any locations where there's not enough supply for sharing, Tesla will just make its own cars and add them to the network in that place. So the current cost of Model 3 Robo-taxi is less than $38,000. We expect that number to improve over time. And we're designing the cars. The cars currently being built are all designed for 1 million miles of operation. The drive units are designed and tested and validated for 1 million miles of operation. The current battery pack is about maybe 300 to 500,000 miles. The new battery pack that's probably going into production next year is designed explicitly for 1 million miles of operation. The entire vehicle, battery pack exclusive, it's designed to operate for 1 million miles with minimal maintenance. So we'll actually be adjusting tire design and really optimizing the car for a hyper-efficient robo-taxi. And at some point, you won't need steering wheels or pedals, and we'll just delete those. So as these things become less and less important, we'll just delete parts. They won't be there. You say like probably 2 years from now, we make a car that has no steering wheels and pedals. And if we need to accelerate that time, we can always just delete parts. Easy. Probably the long term, 3 years, Robo-taxi with deleted parts. Maybe it's being $25,000 or less. And you want a super efficient car, so the electricity consumption is very low. So we're currently at 4.5 miles per kilowatt hour, but we'll improve that to 5 and beyond. And there's just really no company that has the full stack integration. We've got the vehicle design and manufacturing, we've got the computer hardware in-house, we've got the in-house software development and AI, and we've got by far the biggest fleet. It's extremely difficult, not impossible perhaps, but extremely difficult to catch up when Tesla has 100 times more miles per day than everyone else combined. This is the cost of running a gasoline car, or the average cost of running a car in the U.S. is taken from AAA. So it's currently about 62 cents a mile. 13,500 miles from 50 million vehicles adds up to $2 trillion a year. These are literally just taken from the AAA website. The cost of ride sharing is, according to Uber and Lyft, is $2 to $3 a mile. The cost to run a Robo-taxi, we think, less than 18 cents a mile. And dropping. This would be current cost. Future costs will be lower. You say, what would be the probable gross profit from a single Robo-taxi? We think probably something on the order of $30,000 per year. And we expect that we're literally designing, we're designing the cars the same way that commercial semi-trucks are designed. Commercial semi-trucks are all designed for a 1,000,000-mile life, and we're designing the cars for a 1,000,000-mile life as well. So in nominal dollars, that would be, a little over $300,000 over the course of 11 years. Might be higher. I think these consumptions are actually relatively conservative, and this assumes that 50% of the miles driven are not useful. So this is only at 50% utility. By the middle of next year, we'll have over 1 million Tesla cars on the road with full self-driving hardware, feature complete, at a reliability level that we would consider that no one needs to pay attention. Meaning you could go to sleep from our standpoint, if you fast forward a year, maybe a year and 3 months, but next year for sure, we will have over 1 million robo-taxis on the road. The fleet wakes up with an over-the-air update. That's all it takes. You say, what is net present value of a Robo-taxi? Probably on the order of a couple $100,000. So buying a Model 3 is a good deal. Any questions? Well, I mean, in our own fleet, I don't know, I guess long term we have probably on the order of 10 million vehicles. I mean, our production rate generally, if you look at our compound annual production rate since 2012, which is like that's our first full year of Model S production, we went from 23,000 vehicles produced in 2013 to around 250,000 vehicles produced last year. So in the course of 5 years, we increased output by a factor of 10. I would expect that something similar occurs over the next 5 or 6 years. As for sharing versus, I don't know. The nice thing is that essentially customers are fronting us the money for the car. It's great.
So, in terms of one thing is the snake charger, I'm curious about that. And also, how did you determine the pricing? Looks like you're undercutting the average Lyft or Uber ride by about 50%. So I'm curious if you could talk a little bit about the pricing strategy.
Sure. We expect obviously solving for the snake charger is pretty straightforward. It's, from a vision problem standpoint. It's like a known situation. Any kind of known situation with vision is like a charge port. It's trivial. So yeah, the cars would just automatically park and automatically plug in. There would be no human supervision required. Yeah. So that's probably our pricing. We just threw some numbers on there. I mean, I think like definitely plug in whatever pricing you think makes sense. We just kind of randomly said, okay, maybe $1. And the thing is, like, there's like on the order of 2 billion cars and trucks in the world. So robo-taxis will be in extremely high demand for a very long time. And from my observation thus far is that the auto industry is very slow to adapt. I mean, like I said, there's still not a car on the road that you can buy today that is as good as the Model S was in 2012. So that suggests a pretty slow rate of adaptation for the car industry. And so probably $1 is conservative for the next 10 years. Because like people sort of think like there's like actually not enough appreciation for the difficulty of manufacturing. Manufacturing is insanely difficult. A lot of people I talk to think like if you just have the right design, you can like instantly make as much of that thing as the world wants. This is not true. It's extremely hard to design a new manufacturing system for new technology. I mean, Audi's having major problems manufacturing e-tron, and they're extremely good at manufacturing. And if they're having problems, what about others? So there's this on the order of 2 billion cars and trucks in the world, on the order of about 100 million units per year of production capacity of vehicles, but only of the old design. It will take a very long time to convert all of that to full self-driving cars. And they really need to be electric because the cost of operation of a gas and diesel car is much higher than an electric car. So any robo-taxi that isn't electric will absolutely not be competitive.
Elon, it's Colin Rush from Oppenheimer over here. Obviously we appreciate that the customers are fronting some of the cash for this fleet getting built up, but it sounds like a massive balance sheet commitment from the organization over the course of time. Can you talk a little bit about what that looks like, what your expectations are in terms of financing over the next, call it 3 years, 3-4 years, for building up this fleet and starting to monetize it with your customer base?
Well, we're aiming to be approximately cash flow neutral during the fleet build-up phase, and then I would expect to be extremely cash flow positive once the robo-taxis are enabled. But I don't want to talk about financing rounds. It would be difficult to talk about financing rounds in this venue. But I think we'll make the right move. I think we'll make the moves we think we should make.
I have a question. If I'm Uber, why wouldn't I just buy all your cars? Why would I let you put me out of business?
There's a clause that we put into our cars. I think it was about 3 or 4 years ago. They can only be used in the Tesla network.
So even a private person, like if I go out and buy 10 Model 3s, I can run on the network. That's a business now, right?
You're only allowed to use the Tesla network.
Right, but if I use the Tesla network, in theory, I could run a car sharing robo-taxi business with my 10 Model 3s.
Yes, but it's like the App Store. You can only add or remove them through the Tesla network, and then Tesla gets revenue share.
But similar to Airbnb, though, in that I have this home, my car, and now I can just rent them out. So I can make an extra income from owning multiple cars and just renting them out. Like I have a Model 3. I aspire to get this Roadster here next when you build it, and I'm going to just rent my Model 3 out. Why would I give it back to you,
I guess you could operate a rental car fleet, but I think this is very unwieldy. Yeah.
I don't know. Seems easy.
Okay. Try it.
In order to operate a robo-taxi network, it sounds like you have to solve certain problems. Like, for example, autopilot today, if you oversteer, it lets you take over. But if it's if it's a ride-sharing product that someone else is getting in the passenger seat, like moving the steering can't let that person take over the car, for example, because they might not even be in the driver's seat. So is the hardware already there for it to be a robo-taxi, and it might get into situations such as a cop pulling it over where some human might need to intervene? using central fleet of operators that remotely sort of interact with humans, or I mean, is all of that type of infrastructure already built into each of the cars? Does that make sense?
I think there will be sort of a phone home thing where if the car gets stuck, it'll just phone home to Tesla and ask for a solution. Things like being pulled over for, by a police officer, that's easy for us to program in. That's not a problem. But it will be possible for somebody to take over using the steering wheel, at least for some period of time, and then probably down the road, we'll just cap the steering wheel if there's no steering control. We'll just take steering wheel, put a cap on. With the end of like couple modification to the car in order for it to enable that, or we literally just unbolt the steering wheel and put a cap on where the steering wheel handle currently is.
But that is a future car that you would put out. But what about today's cars where the steering wheel is a mechanism to take over autopilot? So if it's in a robo-taxi mode, would someone be able to take it over by just simply moving the steering wheel?
Yes. I think there'll be a transition period where people will be able to take over and should be able to take over from the robo-taxi. And then once regulators are comfortable with us not having steering wheel, we'll just delete that. And for cars that are in the fleet, obviously with the permission of the owner, if it's owned by somebody else, we would just take the steering wheel off and put a cap where the steering wheel currently touches.
So there might be two phases to the robo-taxi. One where the service is provided and you come in as the driver, but could potentially take over, and then in the future there might not be a driver option. Is that how you see it as well, or
in the future the probability of the steering wheel being taken away in the future is 100%. Consumers will demand it.
But initially you would
this is not me prescribing a point of view about the world. This is me predicting what consumers will demand. Yeah, consumers will demand in the future that people are not allowed to drive these 2-ton death machines.
I totally agree with that.
Yeah.
But in order for a Model 3 today to be part of the Robo-taxi network, when you call it, you would then get into the driver's seat essentially, because just to be on the safe. Okay, that makes sense.
Exactly. So, there were amphibians, but then pretty much things just become like land creatures. A little bit of sort of amphibian phase.
Hi.
Sorry, I see what okay.
Yes. The strategy we've heard from other players in the robo-taxi space is to select a certain municipal area to create geo-fenced self-driving. That way you're using an HD map to have a more confined area with a bit more safety. We didn't hear much today around the importance of HD maps. To what extent is an HD map necessary for you? And second, we also didn't hear much about deploying this into specific municipalities where you're working with the municipality to get the buy-in from them, and you're also getting a more defined area. So what's the importance of HD maps, and to what extent are you looking at specific municipalities to roll out?
I think HD maps are a mistake. We actually had HD maps for a while. I actually canned that. Because you either need HD maps, in which case, if anything changes about the environment, the car will break down. Or you don't need HD maps, in which case, why are you wasting your time doing HD maps? So the HD maps thing is like the two main crutches that should not be used and will, in retrospect, be obviously false and foolish are LiDAR and HD maps. Mark my words. If you need a geofenced area, you don't have real self-driving.
It sounds like maybe battery supply could be the only bottleneck left towards this vision. And also, could you just clarify how you get the battery packs to last 1 million miles?
I think cells will be a constraint. That's a subject for a whole separate. There's a whole separate subject. I think we're actually going to want to push our sort of standard range plus battery more than our long range battery. because the energy content in the long range pack is 50% higher kilowatt hours. So essentially, you can make a third more cars if they're all sort of standard range plus instead of the long range pack. The one's like around 50 kilowatt hours, the other one's around 75 kilowatt hours. So we're actually probably going to bias our sales intentionally towards the smaller battery pack in order to have a higher volume of what basically the obvious thing to do is to maximize the number of autonomous units, or the number of maximize the output that will subsequently result in the biggest autonomous fleet down the road. So we're doing a number of things in that regard, but it's just not for today's meeting. The million-mile life is basically just about getting the cycle life of the pack to you need basically on the order, like let's say you've got basic math. If you've got a 250-mile range pack, you're going to need 4,000 cycles. So, very achievable. We already do that with our stationary storage, some of our stationary storage solutions like PowerPack. We're ready to deploy PowerPack with 4,000 cycle life capability. Yeah.
May I ask?
Sorry.
It's
like ventriloquism.
It's obviously significant, very constructive margin implications to the extent you can drive attach rates much higher with full self-driving option. I'd just be curious if you can level set kind of where you are in terms of those attach rates and how you expect to educate consumers about the Robo-tax scenario so that attach rates do materially improve over time.
Sorry, it's a bit hard to hear your question.
Yeah, just curious where we are today in terms of full self-driving attach rates, in terms of the financial implications. I think it's hugely beneficial if those attach rates materially increase because of the higher gross margin dollar that flow through to the extent people do sign up for full FSD. Just curious how you see that ramping. Or what the attach rates are today versus, how do you expect to educate consumers and get them aware that they should be attaching FSD to their vehicle purchases?
We're going to ramp that up massively after today. Yeah. I mean, the fundamental message that consumers should be taking today is that it's financially insane to buy anything other than a Tesla. It'll be like owning a horse in 3 years. I mean, fine if you don't own a horse, but you should go into it with that expectation. If you buy a car that does not have the hardware necessary for full self-driving, it is like buying a horse. And the only car that has the hardware necessary for full self-driving is a Tesla. Like, people should really think about their purchase. Any other vehicle. It's basically crazy to buy any other car than Tesla. We need to convey that argument clearly, and we will after today.
Thanks for bringing the future to present. Very informational time today. I was wondering, you did not talk much about Tesla pickup. And let me give a context for that. I could be wrong, but the way I'm looking at Tesla network, it was as an early adopter and something as a test bed. I think Tesla's pickup may be the first phase of putting the vehicles in network, because the utility of Tesla pickup would be pretty much people who are either loading a lot of stuff or are in the profession of construction or little here and there odd items, like picking up stuff from Home Depot.
Sure.
I would say that, maybe it needs to have a two-stage process. Pickup trucks exclusively for Tesla network as a starting point, and people like me can buy them later. But what are your thoughts on that?
Well, today was really just about autonomy. There's a lot that we could talk about, such as cell production, pickup truck, and future vehicles. But today was just a focus on autonomy. But I agree, it's a major thing. I'm very excited for the Tesla pickup truck unveil later this year. It's going to be great.
Colin Lang and UBS. Just so that we understand the definitions, when you refer to feature complete self-driving, it sounds like you're talking level 5, no geofence. Is that what's expected by the end of the year? Just so we're all on the same thing. And then the regulatory process. I mean, have you talked to regulators about this? This seems quite an aggressive timeline from what other people have put out there. I mean, are they, what are the hurdles that are needed, and what is the timeline to get approval? And do you need things like in California, I know they're tracking miles that, what's an operator behind that? Do you need those things? What is that process going to look like?
Yeah, I mean, we talk to regulators around the world all the time. As we introduce, additional features like navigate on autopilot, this requires like regulatory approval on a per jurisdiction basis. But I think fundamentally regulators, in my experience, are convinced by data. So if you have a massive amount of data that shows that autonomy is safe, they listen to it. They may take time to digest the information. The process may take a bit of time, but they have always come to the right conclusion from what I've seen.
I have a question over here.
And I've got lights in my eyes and a pillar. Okay.
Just wanted to some of the work we've done trying to better understand the ride-hail market. It looks like it's very concentrated in major dense urban centers. So is the way to think about this that the robo-taxis would probably deploy more into that area, and the additional full self-driving for personally owned vehicles would be in the suburban areas?
I think like Tesla owned robo-taxis would be in dense urban areas along with customer vehicles, and then as you get to medium and low density areas, it would tend to be more that people own the car and occasionally lend it out. Yeah, there are a lot of edge cases in Manhattan and say downtown San Francisco, but those are, and there are various cities around the world that have challenging urban environments. But we do not expect this to be a significant issue. When I say feature complete, I mean it'll work in downtown San Francisco and downtown Manhattan this year.
Hi, I have a neural net architecture question. Do you use different models for, say, path planning and perception, or different types of AI, and sort of how do you split up that problem across the different pieces of autonomy?
Well, essentially, right now AI or neural nets are used really for object recognition. And we're still basically just using it as still frames, so identifying objects in still frames and tying it together in a perception path planning layer thereafter. But what's happening is that the neural net is kind of eating into the software base more and more. And so over time, we expect the neural net to do more and more. Now from a computational cost standpoint, there are some things that are very simple for a heuristic and very difficult for a neural net. And so it probably makes sense to maintain some level of heuristics in the system because they're just computationally 1,000 times easier than a neural net. Like a neural net's like a cruise missile. And if you're trying to swat a fly, just use a fly swatter, not a cruise missile. But over time, I would expect that it moves really to just training it against video, and then the video in, car is the steering and pedals out. Or basically, video in, lateral and longitudinal acceleration out, almost entirely. That's what we're going to use the Dojo system for. There's no system that can currently do that.
maybe over here. Just going back to the sensor suite discussion, Elon, one area I'd like to just talk about is a lack of side radars. And it's a situation where you have an intersection with a stop sign where there's maybe a 35, 40 mile per hour cross traffic. Are you comfortable with the sensor suite, the side cameras, being able to handle that? Can you talk about that?
Yeah, no problem. I mean, essentially the car's going to do kind of what a human would do. And you can think of a human as like basically a camera on a slow gimbal. And it's kind of remarkable that people are able to drive the car in the way that they are, because if you can't look in all directions at once. The car can literally look in all directions at once with multiple cameras. So humans are able to drive just by sort of looking this way, looking that way. They're actually stuck in their driver's seat. They can't really get out of the driver's seat. So it's like kind of one camera on a gimbal, and is able to drive. A conscientious driver can drive with very high safety. The cameras in the cars have a better vantage point than the person. So they're like up in the B pillar or in front of the rearview mirror. They've really got a great vantage point. So if you're turning onto a road that's got a lot of high speed traffic, you can just do what a person does, just like turn a little bit, don't go fully into the road, let the camera see what's going on, and if things look good, and then the rear camera's going to show on any oncoming traffic, off you go. And if it looks sketchy, you can just pull back a little bit, just like a person. The behavior is like it starts to become remarkably lifelike. It's like quite eerie, actually. The car just starts behaving like a person.
Over here. Here we go. Ventriloquist, right here.
Okay.
Given all the value you're creating in your auto business by wrapping all of this technology around yourselves, I guess I'm curious as to why you would still be taking some of your cell capacity and putting it into Powerwall and PowerPack. Wouldn't it make sense to put every single unit you can make into this part of your business?
We've already stolen almost all the cell lines that were meant to go to Powerwall and PowerPack and use them for Model 3. I mean, last year, in order to make our Model 3 production and not be cell stopped, we had to convert all of the 2170 lines at the Gigafactory to car cells. And so our actual output in total gigawatt hours of stationary storage compared to vehicles is an order of magnitude different. And for stationary storage, we can basically use a whole bunch of miscellaneous cells out there. So we can just gather cells from multiple suppliers all around the world, and you don't have a homologation issue or a safety issue like you have with cars. So that's basically our stationary battery business has been just kind of feeding off scraps for quite a while. But like, you really think of like production as being, there are many constraints of a massive production system. It's like the degree to which manufacturing and supply chain is underappreciated is amazing. There are a whole series of constraints, and what is the constraint in one week may not be the constraint in another week. It's insanely difficult to make a car, especially one which is rapidly evolving. So, yeah, but I'll just take a few more questions, and then I think we should break forward so you can try out the cars.
Hi, Elon. Adam Jonas. Questions on safety. What data can you share with us today of how safe this technology is, which would obviously be important in a regulatory or insurance discussion?
Well, we publish the accidents per mile every quarter, and what we see right now is that Autopilot is about twice as safe as a normal driver on average, and we expect that to increase quite a bit over time. Like I said, in the future, it will be consumers will want to outlaw. I'm not saying they will succeed, nor am I saying I agree with this position, but in the future, consumers will want to outlaw people driving their own cars because it is unsafe. And think of like elevators. Elevators used to be operated on a big lever, like you go up and down the floor, and there's like a big relay, and you had elevator operators, but then periodically they would get tired or drunk or something, and then they'd turn the lever at the wrong time and sever somebody in half. So now you do not have elevator operators, and it would be quite alarming if you went into an elevator that had a big lever that could just move between floors arbitrarily. So they're just buttons. And in the long term, again, not a value judgment, I'm not saying I want the world to be this way. I'm saying consumers will most likely demand that people are not allowed to drive cars.
Elon, a follow-up. Can you share with us how much Tesla is spending on autopilot or autonomous technology by order of magnitude on an annual basis? Thank you.
It's basically our entire expense structure.
Question on the economics of the Tesla network, just so I understand. It looked like, so you get a Model 3 off lease, $25,000 goes on the balance sheet, would be an asset, and then you it would cash flow $30,000 a year. Roughly, is that the way to think about?
Yeah, something like that. Yeah.
And then just in terms of the financing of it, there was a question earlier. You mentioned you would do it. Is it cash flow neutral to the Robo-taxi program, or cash flow neutral to Tesla as a whole?
Sorry, the cash flow neutral.
In terms of, he asked a question about financing the Robo-taxi. It looks to me like they're self-financing, but you mentioned they would be basically cash flow neutral. Is that what you were referring to?
No, I just think between now and when the Robo-taxis are fully deployed throughout the world, the sensible thing for us is to maximize rate and drive the company to cash flow neutral. Once the Robo-taxi fleet is active, I would expect to be extremely cash flow positive.
And this, so you were talking about production.
Yeah.
To produce them. Okay, thanks.
Maximize the number of autonomous units made.
Thank you.
Okay, just maybe one last question.
Yeah. If I add my Tesla to the Robo-taxi network, who is liable for an accident? Is it Tesla or is it me? If the vehicle has an accident and harms.
I mean, it's probably Tesla. It's probably Tesla. I think the right thing to do is to make sure there are very, very few accidents. All right. Thanks, everyone. Please enjoy the drives. Thank you.
Thank you very much.